Good morning, class. We are looking at Chapter 3, Derivatives. Here's Section 3.7, Derivatives of the Logarithmic Functions. So we've covered derivatives and rates of change, the derivative as a function, basic differentiation formulas, the product rule, the chain rule, implicit differentiation, related rates, and now derivatives of the log functions. This is the synopsis of that. We're going to go over it in a moment. So first, reminding you of various differentiation formulas, starting with the definition: f prime of x, the limit of f of x plus h minus f of x over h as h approaches 0. The derivative of x is 1. If you have a constant, you can take it out. It's a multiplier. If you take the derivative of the difference, you get the difference of the derivatives. And these are some basic differentiation formulas, such as the derivative of a constant is 0. The power rule, one of the most useful formulas, the derivative of x to the power of n is nx to the power of n minus 1, and trigonometric functions. Two ways to define E. E is a number such that the limit of 1 plus 1 over n to the power of n as n approaches infinity. Okay. Or E is such a number that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. This one is really this derivative of the constant times a function. These two are exactly the derivative of the sum and the difference. And product rule, quotient rule. Exponential functions, the derivative is always itself, and then you use the chain rule or change of base or logarithmic properties times L and B. And composite function result in the chain rule in two different formats. If it's f of g, the derivative is f prime of g of x times g prime. In the Leibniz's notation, dy dx is dy du du dx. And if we go back to the power rule, the extended power rule, the derivative of g of x to the power of n would be n g of x to the power of n minus 1 times g. So this is the synopsis of differentiation formulas. Everybody should be comfortable. Also, I want to remind you of logarithmic properties. We're going to need it in this section. B, the base must be positive and it can't be 1. If y equals log base b in this case, then it's equivalent to x equals b to the power of y. In other words, if you look at these two cases, they both have the same exponent y, the same base b. And to have an understanding of that, let's look at the arrow here. Log x base b equals y means b to the power of y equals x. As long as we can make one format into another one back and forth, we're going to be having an easy time with the properties I'm going to discuss and remind you. So y equals log x base b means b to the power of y equals x, and this is the general case. B is any number as long as it's positive and it is not 1. Log 1 with any base is 0. Log b base b, that means the base and the argument are identical, is 1. Log base b of b to the power of x is x. B to the power of log x base b equals x. And this is the product rule. Log x y base b is log x plus log y, both of them base b. Log of x over y base b is log x minus log y, both of them base b. This is the quotient rule. And finally, the power rule. Log base b of x to the power of n, you put the n in front, becomes n log x base b. And first of all, notice this arrow here. Secondly, these two refer to the fact that logarithmic functions and exponential functions are inverse of each other. Now, if the base is 10, instead of writing log x base 10, we're going to write log log x, no base. That means the base is 10. And therefore, these properties become what you see. For example, the first one just dropped the base. But the second one, If you know the base is 10, then the argument must be 10 as well. This one, the same thing, the base is 10, so 10 to the power of x. This one, the base is 10, so 10 to the power of log x must be x, and these three basically drop the base b. When the base is e log x base b, we write it as y equals ln x, which means e to the power of y equals x. And of course, instead of log, we would use ln. So ln of 1 is 0. So if you look at this one, when you write ln, the base is e, so ln of e equals 1, and the rest of them follow. Because exponential and logarithmic functions are inverse functions, they are symmetric with respect to the line y equals x. So if you pay attention to the x-intercept here, 1, 0, okay. And by the way, this is the change of base formula. Log x base b is log x over log b with any base a. We either choose common log or natural log for the sake of calculation. So going here, when x is between 0 and 1 here, this goes below and it becomes negative if x is larger than 1. That means here you're looking at this piece, and natural log is positive. All right, let's look at some warm-up examples regarding logs. So what is log of 81 base 3? If we don't know, we say, okay, what about x? And you perhaps know 3 to the power of 4 is 81, therefore the answer is 4. However, if you don't know that, this is the way you are going to work it out. Well, from here, you are going to write 3 to the power of x must be 81. And again, you should know 81 is 3 to the power of 4, x becomes 4. Part B, what is it? Some variable, x, y, z, you choose it. And perhaps you know 25 to the power of 1/2 is 5. That means the square root of 25 is 5. So the answer is 1/2. And if we don't know, again, we're going to go with the arrow with a different color. Let me go with 25 to the power of y equals 5. We know 25 is 5/2. 5 squared, my apologies. And on the right side, when we have no exponent, the exponent is 1. So the left side is 5 to the power of 2y, 5 to the power of 1, 2y is 1, and y is 1/2. This is in case you want to go through it from A to Z. Now, this one has 3 decimals, so it's -3, or 10 to the power of -3 is 0.001. And I want to remind you, log 10, it has 1 0, it's 1. Log 100 has 2 zeros is 2. Log of, let's say, 100,000 has 5 zeros. Let me 1, 2, 3, 4, 5. So it's 5. Log of 0.1 has 1 decimal, -1. Log of 0.01 has 2 decimals, -2. In this case, we have 3 decimals. Just to remind you how you deal with powers of 10 and logs. We want to write this in exponential form, and all we have to do, go with the arrow, everybody. 5 to the power of 4. So log base 5 of 625 equals 4. That means 5 to the power of 4 is 625. Log 49 base 7 is 2. 7 squared must be 49. Log 81 base 1/3 is -4. That means 1/3 to the power of -4 must be 81. Log 3 base 81 is 1/4. That means 81 to the power of 1/4 must be 3. And obviously, 1/2 to the power of -5 must be 32. What about those? Again, go with the arrow. Ln, you don't see any base, you know the base is e, so e to the power of t must be s. Log, you don't see any base, the base must be 10, 10 to the power of q must be p. This is just to remind you how things work. And of course, the expectation is that you're very comfortable with those. If you're not, make sure you practice because we are going to need them for this section. So having said that, section 3.7, derivatives of the log functions. We want to differentiate y equals ln x, and we don't know how to. We haven't done that. However, we know how to write it in an exponential form. E to the power of y is x, and that we can differentiate implicitly, everybody. So, what is the derivative of any exponential is itself? And remember, y is a function of x, or like g of x. So e to the power of y times y prime, or dy dx. And x, the answer is 1. So y prime is 1 over e to the power of y, or 1 over x. So we proved if y equals ln x, its derivative just flip over the argument. So we can extend that to anything, and also the chain rule. Therefore, ln of absolute value of x is 1 over x, x can't be 0. I want to explain about this one, y absolute value, because the domain for basic log is from 0 to infinity, all positive values. The derivative of ln of g of x is 1 over g of x times g prime, and g of x must be positive. That takes care of that absolute value thing. And of course, x can't be 0. d dx of, if instead of g of x you call it u, it's 1 over u du dx, and of course u is positive. So that is the assumption that the value of u is positive, and then we are going to move on. So to differentiate this, following the rule, the derivative of ln of g of x, flip it over times g prime by the chain rule. So y equals ln of 5x minus 1. Just flip that over. 1 over 5x minus 1. By the chain rule, we need its derivative, which is 5. And we just rewrite y prime as 5 over 5x minus 1, and we are done. Y equals ln of x cubed. There are two ways to do that, and I'm going to do both ways. Number one, just the way it's given, this is your g of x, everybody. This is the g function. Flip this over. 1 over g of x. Y prime is 1 over x cubed times g prime. The derivative of x cubed, 3x squared. And you can see that 3x squared over x cubed is 3 over x, and you're done. However, the second method, and in this case, it makes not much of a difference because this is not complicated. You use number 7 and number 3 becomes the coefficient. And now, when you want to differentiate this 3 is a multiplier, you just do ln x, which is 1 over x. So 3 times 1 over x, or 3 over x. As I mentioned, it did not make much of a difference in this example. However, it does when it gets more complicated. For example, if you want to differentiate this just the way it is, 1 over g of x means do what? Write the reciprocal of this. Then G prime means what? Differentiate this using the quotient rule. Don't do that. Instead, first we start with number 6, and you can do that in one shot, but let's do it in two. So let's start with number 6 and say ln of the top minus ln of the bottom. And then that was the quotient rule. And then use the product rule on this piece, ln2 plus lnx. In other words, decompose the log 100% to make it nice and easy. So I want to differentiate. Now, ln2 is a number. So the derivative is 0, and ln x is 1 over x. So ln2 gives you 0, ln x gives you 1 over x. And this one is minus ln of g of x, 1 over g of x, flip it over, 1 over 2x plus 1, and g prime, the derivative is 2. And believe it or not, this is the only calculus step. Everything else is algebra, logarithmic properties from algebra. So I'm going to rewrite this so it becomes clear that we have 1 over x minus 2 over 2x plus 1. Now, LCD means x times 2x plus 1. 1 times 2x plus 1 minus 2 times x. That would be the numerator. I'm assuming nobody has any problem evaluating fractions. So we get 2x plus 1 minus 2x is to cancel each other. And the final answer is f prime of x equals 1 over x times 2x plus 1. As you can see, decomposing it first makes it very easy, one easy calculus step. Y is 5x times ln of x squared. I want to concentrate on that. And number 7. The power rule first, I'm going to put the 2 here. So it's 5x times 2 ln x, and of course 5 and 2, 10 x ln x. You have a choice of keeping the 10 outside and deal with x times ln x, or 10x is f, ln x is g, and we use the product rule. F prime g plus g prime f. So 10x, the derivative is 10 times g ln x plus g ln x, the derivative is 1 over x times f, which is 10x. Clearly, this changes to 10. You can factor number 10 out. So 10 times ln x plus 1. Y equals ln x over x, we are going to call it f over g and use the quotient rule on that. So f prime g minus g prime f over g squared. F prime is 1 over x times g, which is x, minus g prime, which is 1 times ln x. And just write the bottom and square it. G squared becomes x squared. Now, clearly, when you multiply these two, you just get 1. So 1 minus ln x over x squared is the final answer, everybody. All right, we want to differentiate y equals ln of 3x times x plus 4 to the power of 5. And we're going to use the product rule and then the power rule. So this is ln of 3x plus ln of x plus 4 to the power of 5. Ln of 3x is ln 3 plus ln x. That means I'm using the product rule again. And this one, you put the 5 in front, I'm using the power rule. So ln 3 plus ln x plus 5, ln of x plus 4. To differentiate, ln 3 is a number gives you 0, ln x gives you 1 over x. To differentiate this plus 5, just remains it's a multiplier. And you want to take the derivative of ln of g of x, so 1 over g of x or 1 over x plus 4, times its derivative g prime, which happened to be 1. So what we are dealing with is 1 over x plus 5 over x plus 4. And we want to add these two. We take the LCD, which is x times x plus 4. And this would be 1 times x plus 4. This would be plus 5 times x. That would be the numerator. One more time. 1 times x plus 4, 5 times x. This is elementary algebra, basic math. You should be able to do that. So we have the following. X plus 4 plus 5x. X and 5x, they add up to 6x. And therefore, y prime is 6x plus 4 over x times x plus 4. That is the final answer. All right, we want to differentiate y equals e to the power of 2x times ln x. And we notice it's the product of e to the power of 2x and ln x. We use that, the product rule. E to the power of 2x. So we want f prime, and any exponential, the answer is itself, e to the power of 2x. And by the chain rule, we need the derivative of 2x times 2. So that's f prime, and then times g by the product rule times ln x. And then g prime is 1 over x times f e to the power of 2x. So this is f prime. Let's just write it. F prime g plus g prime f. And you can clearly see that e to the power of 2x is in common. If we take it out, this gives us 2 ln x. This gives us 1 over x. And that is the final answer, everybody. We want to differentiate y equals log base 3 of square root of x. And so what we are dealing with is log, but it's not a natural log. So how do we deal with that? Well, when y is log x base b, we can use the change of base formula to write it as ln x over ln b, which means it's the product of 1 over ln b and ln x. 1 over ln b is a number, is a coefficient. So when you differentiate this, this doesn't change. You just differentiate ln x. So y prime is 1 over ln b times the derivative of ln x, which is 1 over x. And you rewrite it as 1 over x ln b. So we're going to do the same thing here. However, we notice this is the square root of x. We're going to rewrite it as x to the power of 1/2. Using number 7, the power rule, we're going to put the 1/2 in front. We have completely decomposed the log, and now we are going to use differentiation. So to differentiate this, first and foremost, number 1/2 remains as a coefficient, as a multiplier. So you got to flip this over, 1 over x. And then when you look at the base is not e, then you need 1 over ln b, 1 over ln 3, and rewrite it. Y prime is 1 over 2x ln 3. You keep the 2x to the left, because if you put it next to 3, one may think it is 3 times 2x, which is the argument of log, and it's incorrect. What about this one? I hope you realize what we are really adding to this concept is that this is a function of x. In this case, we didn't need the chain rule. In this case, we do. Therefore, the derivative of log base b of f of x, because we are dealing with log, we're going to flip this over 1 over f of x. Because this is a function of x by the chain rule times f prime of x, because the base is not e, 1 over ln b, and that's it, you put them together. 1 over fx ln b times f prime of x. So this one, the first thing first, can we decompose? The answer is no, so deal with it the way it is. Number 1, 1 over f of x, this is your function. So 1 over the argument. Number 2, by the chain rule f prime of x. So the derivative of that is 2x times 2x. And finally, you look at the base is e, no, therefore 1 over ln b, 1 over ln 5. And of course, it's a fraction with the 2x at top only. So f prime of x is 2x over parentheses x squared plus 1 times ln 5. So that's pretty straightforward, everybody. Y equals ln of sine x. We want to differentiate that. So again, just write the formula from the scratch, from the memory. And according to this, the derivative of ln of g of x, 1 over g of x. Flip this over, 1 over sine x. Times its derivative. The derivative of sine x, or the argument of log, is cosine x. Now, what is cosine x over sine x? I want to remind you of some identities we already discussed in trigonometry. Tangent is sine over cosine, the same as 1 over cotangent x. Cotangent x is cosine x over sine x, the same as 1 over tan x. Secant is 1 over cosine x, and cosecant is 1 over sine x. Therefore, cosine x divided by sine x equals cotangent x. Y equals ln of 5x. If it helps, write this one as g of x. In other words, g of x equals ln of 5x. So now we're going to go with this formula, 1 over g of x. So 1 over ln of 5x times g prime. Now, this is g, differentiate this. Differentiate ln of 5x. To differentiate ln of 5x, again, you have to use this. So 1 over g of x, 1 over the argument, 1 over 5x, and then g prime, the derivative of 5x is 5. I hope you see what happened. One more time. First, you flip this over, 1 over ln of 5x. Then to differentiate this, you flip this one over, 1 over 5x. And then by the chain rule, the derivative of that is 5. As you can see, the numerator has 5, the denominator also has 5. We are going to get rid of those. So the numerator remains as 1 and only 1. The denominator is the product of ln of 5x and x. We put the x in front, and y prime becomes 1 over x ln of 5x, everybody. Y equals 1/2 ln of 1 plus x over 1 minus x. If you differentiate the way it is, you keep the 1/2, you have to flip this over, and then you have to differentiate this using the quotient rule. We're not going to do that. We are going to take the easy way out by decomposing the log first, meaning 1/2 remains, and this piece use the quotient rule of logs, ln of the top, 1 plus x, minus ln of the bottom, 1 minus x. So we decompose this. That makes it a lot easier now. How do we differentiate this? So y prime is 1/2. You keep the 1/2, and you're going to differentiate this one and then differentiate this one. To differentiate this one, we are going to go with the derivative of g of x, ln of g of x, which means we are going to flip this over. 1 over 1 plus x. 1 over g of x, 1 over 1 plus x times g prime. The derivative happened to be 1, but I highly recommend you write it. Minus 1 over g of x again, minus, flip this over, 1 over 1 minus x times g prime. Now the derivative of the parentheses this time is -1 times -1. I'm going to box this. Because this is the only calculus step. This was algebra using logarithmic properties. This is calculus. Now we're going to combine these two fractions, which means we take the LCD and we continue with the work. Every other step is basic algebraic step. So first and foremost, the 1/2 outside remains. Let's rewrite this as 1 over 1 plus x, because this has no bearing, 1 times 1. But this one, -1 times -1 makes it plus 1 over 1 minus x. So one more time. The first fraction is itself. The second fraction, negative and negative, results in plus 1. So you're adding these two fractions, which means, again, 1/2 remains. And LCD means just multiply these two. So 1/2 remains. LCD is the product of 1 plus x and 1 minus x. To combine the two fractions, 1 times 1 minus x plus 1 times 1 plus x. So 1 times 1 minus x plus 1 times 1 plus x. And we're going to simplify the numerator. We get 1 minus x plus 1 plus x minus x plus x, they cancel each other. 1 and 1, they add up to 2. So we have 1/2 times the fraction. The numerator is 2. The denominator is 1 plus x over 1 minus x. First of all, these two cancel each other. The numerator becomes 1. Secondly, these two, a plus b, a minus b is a squared minus b squared. So it's 1 minus x squared. Again, let me just quickly write that. A plus b, a minus b is a squared minus b squared, which means 1 squared is 1 minus x squared.